the operating system we are going to create is also a real operating system. All right, so let's describe this project. I'm going to do it very differently from everybody else, because if you have watched any videos or read any books about coding an operating system, people usually start with the really low-level stuff. But I don't think that's very beneficial for you guys, my viewers, my subscribers or members, because it's very difficult to test that. You need to create a virtual machine and write a disk image and a whole lot of different things. And we are going to do all of that. But during development, we are going to run this on top of Windows or macOS or Linux. And I'm going to show you how it's going to work, because this project is divided into 3 different projects. So if we start closest to the user, let me just draw a perfect rectangle. It's nice. And let's do another one. Okay, that wasn't as nice. But I will not get stuck on aesthetics today. All right, so these are the 3 components of our project. So the thing to the left, let's say the user is closest to the right. And so is like the monitor and the keyboard and well, perhaps a mouse. Why not one of these old school mice with 3 buttons like this? Never mind. Let's stick to what's important. So this thing to the right, I will call the following. Command.com. So this will be the command prompt, basically. So the user will be welcomed with a prompt in something like the following. So C and a colon and a / and then this character, and then they have this blinking marker that they can use to write commands. So that is command.com. And what is that going to, what kind of responsibilities is that going to have? I'm going to list a little bit more than what I'll be doing at first, but let's start with the 2 most basic things. It needs to read commands from the keyboard. So let's do it like this. So read command from keyboard. So this is one of the primary tasks, and the other is when they run these commands and execute the programs and whatnot, it needs to print the results to the standard out or to the screen. So let's write that as well. Print the results to screen. That's it. All right. So now we have 2 different things. Let's highlight in different colors so it becomes a little bit more intuitive. So read will be pink and print will be green. All right, so this is the most important things about this command prompt. And by the way, this sketch that I'm doing right now, this is it's during development. So there will be changes when we go to production, but during the most part, like probably 90%, um, this will be the thing that we are working with. All right, and then we have this other pillar in the middle here, um, and this I call the OS API. And if you don't know what an API is, it's basically a set of functions um, that you export from a library. So the user of that library will not need to know the internals of that specific library. All they need to know is that they call the function with a specific name, so on and so forth. So this OS API will be the glue, so to speak. It will handle all the things that we can't handle directly in userland. So like file I/O and reading and writing, screen, keyboard, exiting the program perhaps, at least early, and opening files and directories and listing the content of directories and so on and so forth. So everything that in Linux, for example, is called system calls. Those we will have inside of the OS API. And if we, to the right here, focusing on function calls, inside the OS API, we do API calls. So if we, for instance, wishes to read one character from the keyboard for standard input, then we're going to use an exported function from the OS API, an API call, which is named load. So let's do this one pink as well. So this load function will read one character from a file descriptor. So we will have a concept of file descriptors. It will work a little bit differently than POSIX, for instance, but quite similar. So we open a file, we get an integer back, and we give that integer to load, and then it will read one character and return it. Simple enough. No need to use an alternative strings and so on. Always 1 byte. And then we will have another API call, which is called store. And as you might grasp, this will write one character to FD, which means that this will be our green thing here. Because if we write to the standard output, we will print it to the screen. So we can easily make these connections. These two are linked together, and these two are linked together. So basically it's just another set of functions that we use instead of the regular system calls. And I'm going to tell you real soon why that is a good way to build this thing. And what do we have farther to the left here during development? So these two to the right, they don't change when we go to the next step. The only thing that will change is this to the left here. So at this point during development, this will be Windows, it will be Mac OS, or it might be Linux. So maybe you are starting to understand why this is such a great way of developing this thing, especially when you follow along in the video. Because while we are developing this command prompt and this OS API, it will run on your regular system, so Windows or Mac or Linux, and it will do that all the way to the last phase of the project. So if we have functions to the right, we have API calls in the middle. To the left here, we have regular system calls, which means that this load function, for instance, that will read from the keyboard in POSIX, which is a standard that all these systems support, this system call is called read. And it's usually depicted with a 2 inside of a parenthesis, and that's to indicate that it's a system call. If it's a library call, there's 3 there instead. But that's only how you express it. So in this sketch, the read syscall is going to be the pink one, which connects to the load and connects to the reading from keyboard inside of the command prompt. And as you might have guessed, there is also a write system call. And in our sketch, this will be our green thing connecting to door function. Yeah, so all the API calls will be mapped to the POSIX standard system calls inside of Windows, macOS, or Linux. So through the whole development, you will be able to follow along on your regular system. Pretty nice. And one note, you need to have a POSIX compiler. So if you run Windows, for instance, you should download something called Cygwin, and there are others as well, but Cygwin works with all of this code floor, and it has the exact same commands like GCC for compiling and stuff as I do on Linux. So you can just type what I type and it'll work. For macOS, then you need to install GCC somehow. I think there is a macOS toolkit which is called Brew or Homebrew, and you can use that to install GCC. And on Linux, well, I have not seen many Linux distributions that have a package with a GCC compiler. So this is during development, right? What about the real low-level stuff? We are coding a real operating system. So we're not just going to code a command prompt or some API library. We are going to code an OS, which means that when we are done with both of these write sections, then we will do this. So let me just clean this up a little bit. That's not cleaning. Here we go. So I'm going to remove the headline and this whole thing to the left here. Okay, so the last phase is creating all the real low-level operating system things. So let's draw another of these rectangles. Not good enough. So let's see. So now we are at the low-level OS. And this is primarily divided in two different parts, with one part being much smaller than the other. So the thing on the top here is what's called a bootloader. So when you start your computer or a virtual machine, you need a bootloader which actually finds the information on your hard disk drive, what operating system you wish to run. And then it should launch that operating system. So a bootloader is the first thing that we need to do at this level. And a bootloader is always programmed in assembly. I don't think it's even possible to do it in another language. The rest of this so far is C only. And then we have, and that is called the operating system kernel. I'm sure you have heard of that word before, like the Linux kernel and such. And the kernel is programmed in assembly, but also in C. There is a possibility to do some of the work in C. So now we're not at the system call level any longer. Now we are at the doctor calls. So a doctor call is what I call a system call, basically. But it's my own system calls that's programmed inside the operating system kernel. So in order to differentiate those system calls with my system calls, I will name these doctor calls. So if we want to see an example how one of these doctor calls is invoked, let's say we want to run this load. Let's see. Yeah, let's run the load API call and thus the doctor call. And in assembly, this is done like this. First, we move into EX, and here got a number, and that is the number of the doctor call. So we will have some kind of a list. So let's say we have a doctor calls.h, and then inside of this file we will have a couple of definitions. So we are going to define, and all the doctor calls, their identifiers, start with dr. So this would be dr load, and then we give number. So this may have the number, I don't know, 2 perhaps, and then the list continues on like this. So then we have doctor store, and that might be, let's say 4, and so on and so forth. So that means that in this case we move into EX, the number 2. So that's how we decide at the low level what system call we want, vector call we want to call. Then we need to push the argument as well, because the load function will take one file descriptor as an argument. So the first argument will, same as in the calling convention of regular x86, we move it into EBX, and let's say we are reading from standard input. In this case, we will give this a 0, because 0 is standard in. And then we need to execute an instruction which will do the actual call. So we will do an interrupt, and the interrupt is going to be the same each time. It's going to be 0x doctor. And I know it's a little bit off the rails, making D7 DR, but if you think about it, an R looks like this, and if you look inside of a mirror, let's say, it can look like this. So it's easy to remember that way. Always D7 to execute the call. Alright, so this is the high-level view of the low-level operating system, so to speak. We also need to create a list of different things that we need to do at this level. So let's just write a couple of things. First, we need to have the bootloader, so we can load our operating system. After that, we need to be able to use BIOS interrupts. So basically, in the same way that we have used it here, the interrupt, to give control over to the inner workings of the operating system. The same is done for the computer through the BIOS. So there are a list of BIOS interrupts which one can use to print things to the screen and do colors and communicate hardware and so on and so forth. So that's a bit of it. And we are going to use these interrupts to read from the hard disk drive. So we need to be able to use a file system, and I haven't yet decided on which one. Maybe I will create my own even. When we are able to open and read files through the file system, then we can continue on and load our kernel. So basically we just read the whole file containing the code for the kernel, the assembly instructions. We put it inside of the memory somewhere and we jump to it. Then we need to set up our own interrupt handlers. And that's so we can use these doctor calls, for instance, and maybe some other ones as well. And this really tedious work is setting up these interrupt handlers. It's a lot of repetition and a lot of filling in different structs with numbers and stuff like that. So let's save those things for last. And we do also want to be able to use the VGA, so we can communicate with the monitor, handle colors and write to specific portions of the screen. And possibly, I haven't yet decided, we might want to set up paging as well. So paging is basically a way to handle the memory, because the memories have been so huge the latest couple of years that we can no longer reference all of that in just 32 or 64-bit point. So basically each process will have its own complete address space, and then the kernel will map those different areas to real memory addressing. But it's strictly not necessary in our case, because we are not recreating Windows, we are recreating DOS, which is a 16-bit OS. So we will only be able to handle 65K of RAM. So paging is not really something we have to worry about, but if we have a lot of time on our hands, which has never happened as of this far, but anyway, I'll put it on the list. And we also need to do the low level I/O. So low-level input and output, reading from files and network devices and from the keyboards and other hardware, and writing to them as well. So this is not an exhaustive list, but it's a few of the most important things that the operating system has to deal with. But to tie this back to what we had before, when we were at the developing stage, we were linking this load OS call and this store OS call to two different POSIX syscalls. But inside of this low-level operating system, we are going to rewire the API. So basically, we will have a similar thing here. We are going to have a load doctor call and store doctor call. And as you can imagine, this store is green and will be wired to this store in the middle, and this load will be pink and wired to this. So that's the beauty of this API layer. It's a little bit extra work, but the upside is that we can code almost the whole project directly on our Windows machine. And then at the end, all we do is rewire this API. So instead of letting load point towards the read system call, it will call this load doctor call instead. And that's it. So when we have written the kernel, or the start of the kernel, and the bootloader, we can just switch off this left layer. Alright, so this is the general idea, and to put this headline back, the last one was during development. This will be during production. It deserves to be highlighted with a yellow pencil, I think. Okay, it's a lot of moving parts. I hope you got the lion part of it anyway, and that you appreciate this way of building the project. So we will focus on all the fun stuff today and in the beginning, the first episodes, because writing this command.com be really interesting. Also, this API layer will be very interesting to write. And when we get to all the assembly stuff and the tedious filling of structures and numbers inside of C, we only have a couple of steps left to have an entire operating system. And this is not going to be a toy operating system. This is going to be our own version of MS-DOS. So it's not going to be compatible with the programs inside of MS-DOS, but we will be able to compile programs for our own Dr. DOS. And my hope is to implement as many as possible of the DOS commands. So just to mention a few of them, you probably know a couple, but we use the cd command to change into another directory and folder. Cd without any arguments will just print the current directory. We use the dir command to list the contents of the directory, so the different files and subdirectories, and some information like file size and whatnot. What else do we have? We have echo, which prints something on the screen. If we wish to start the program in the current directory, say, let's say we have a program which is called I don't know, firewall, then we can either just type firewall or we can type the entire file name, which is firewall.com. We're not going to have support for exe files, because I don't really see the point of having two different executables. And the .com format is very simple. It's just a long list of instructions to the CPU that you load into memory and jump into it. So we will have something similar to that. But they, as I mentioned, they will not be compatible with the MS-DOS.com files because we have different system calls. And then there are different commands which are useful when you do script. And scripts, I think we should support. They are called bot files. It stands for batch files. So basically you will do a batch of several jobs or similar. And there's a for command which you can use to iterate through a list of files. And what else? It's you can set environment variables like the path with the set command. And then we have the copy command, which will copy a file. And you can also do copy con, and that means that you are copying the content that you type on the keyboard into a file. And then there's move if you want to move the file, and there's the ren if you want to rename it. It's del if you want to delete it. There's also rmdir for removing the directory. A lot of things. And as I mentioned, we will not be using the backslash because it's annoying that all other big systems use the forward slash, and it's a compatibility issue when you code for multiple operating systems. So let's do the forward slash instead. But when we use some of those commands, so let's say we do dir /s and then the name of a file, say. So let's say, I don't know, ABC. So this is a switch /s, and it means in this case that we search all subdirectories as well for the file. But we cannot really use slash for these switches since we already use the slashes for anything else. So I will do a regular dash instead. So dash s. All right, that's a very deep introduction to this whole project. But I think it's necessary to know all of these things before you start, so you don't just code in blindness and they don't understand what you're building, the big picture. And maybe you didn't understand this, at least all of this, while just listening to this once. I recommend when you have watched this entire episode, watch it again and rewind, so you make sure you understand everything. Because this is a very, very good project to have done, to have finished for your resume. All right, so the next 2 hours or something like that, we are going to start implementing this command prompt and this API layer. And we want to make at least load and store work linked to what we had here before. So the system calls read and write. Hopefully we can achieve that in 2 hours, including any troubleshooting. Started.
Sup guys, welcome to today's show. So let's create our own operating system, shall we? And this will be three parts. The first will be the low-level operating system, but we're going to start with part 2 and part 3. And this will run on Linux and on Windows and on macOS while developing. So the second part I'm going to call OS API. So I will do bash bs OS API, and I will use the default C template. And if you don't have bash bs installed, you can find it at the repo.drbirch.com. You can also check the video which is called Coding a Build System. And the third part will be the command prompt. So I will call this command and also the default C templates. So I'm going to open up these folders. Let's see. DDoS, I will call it, Swedish pronunciation. And that stands for Dr. DOS, Disk Operating System. So I will open this in VS Code. So now I have these two folders, and I'm going to start by editing the Makefile a little bit. I'm going to use the C23. If you don't have the latest compiler, you can use C2X, and if that doesn't work, you can remove this part. And I will remove Birch utils from the link flags because I can't use any libraries. I can't even use the standard C library because I'm coding an operating system. So we need to do everything ourselves. We will not even be allowed to use system calls. And that's why I have this OS API, which will take care of the translation of system calls. So I will do the same for this, like so. And I'm going to open up all of these. So Command C and OS API and the 2.h file. And I'm going to change this up a bit. I'm going to use the number of bytes for these. And same here. Like so. And I need to remove Birch utils. And, well, I need to remove all of these as well. I will, however, for now, keep the stdio because I might need printf while developing to make things a little bit easier. But that's all. So we'll only have this stdio.h. And I can remove this definition as well. Alright, so let's see. in the OS API, I'm not gonna have a main function because this will be a kinda library, not a regular shared library, but something similar. So I need to change this makefile. I only need to, let's see, I don't need to do a binary executable. So the only thing is osapi.o. Like so. And let's see. Inside of the makefile for the command project, I'm gonna change this up a little bit. I'm gonna call the executable command.com. And we're gonna link in OS API, OS API.o, like so. And I'm gonna create an additional .o file in this project, which I will just call os.h. And this I'm gonna put inside of the include file of command.h. So I'm gonna do include os.h and update this so I have the include directory of OS API. Alright, let's see if this will compile. Forgot to remove main inside of the C. There we have command.com. Alright, so now we have the basic setup of our program or operating system. So how do we do this? Well, we need to be able to input a command because our OS will be pretty much like this command window right here. We're gonna have a prompt saying what directory we're in. We're gonna do commands like dir for printing the files in the current directory. We're going to be able to change directory with a cd command, and so on and so forth. So the first thing we're going to need is the ability to read a command from the user. So let's see where we start. I think we're gonna start so we have an ability to print something to the screen. So I want to have a doctor call. I'm going to call my own system calls doctor calls. So let's see. I want to include os.h here as well. Alright, so we're gonna have a function called, let's see, store and load. So I think we're gonna have it as a bool. We're gonna call this one store, which will write something to either a file or the screen or somewhere. And it's gonna take a file descriptor. Let's see, an int16, and then we're gonna have a single byte, and that's it, I think. And we're gonna have a load as well. Let's see. No, this should be called load, and maybe I can do this. No, this is write one char, and then we're gonna have something which reads one char, so it will return that char. And this will be called store, and it's going to take a file descriptor and nothing else, I think. So these are the first two things inside of our API. And we don't have the bool data type. Maybe we can do something like if we define bool as an int8, and we define true as a 1 and false as a 0. And I think we need to move these to here. right? So let's create these functions, the load and the store. So this will be inside of the OS API. So it'll be bool store, and it takes an int16 file descriptor, and it takes 1 character. Maybe we should have an own data type for file descriptors, actually. So this will be a file descriptor, and this too. Then we need to name it something else. Let's say file. Alright, so since we cannot use the standard 0 for standard input and 1 is etc., we're gonna need to define our own such things. So let's see. If file is more than 1, which means it's not standard in or out, we're not going to use standard error. In that case, we need to check that the file is open. And in that case, we need to produce an error. So let's say we do return error, and it's error bad file descriptor. And what is return error? We need to define that. So define return error. It takes an argument, and we're going to do and we're going to set the error number, which we need to define ourselves, to whatever x is. and then we're going to return 0. And we'll do this while false trick. So we have a loop, but it will not loop. We just have this so we can have it inside of these brackets. And we need to define the errors and the error number. So let's do define r bad fd, and let's start with 8, because we will probably have some errors which are more common, and I want them to have the lower representations. Okay, and we need this error number as well. So where do we put that? Here maybe. So this will be an int 8 error number. Maybe even an own data type called error. So we type def an int 8 to error. And why is this red? Comment unclosed. Is it? That's weird. Oh, never mind that. All right. So we return an error if the file isn't open, and we need to create this is open. And since this is a local function, we're not going to put it inside of os.h because this is exported stuff. So let's go here and let's see. So we're gonna have a bool is open, and it's gonna take a file descriptor. And I think we're gonna mark functions as either exported or not. So let's say this is a private function. And these are public functions. So let's define public as, let's see, we can use the attribute and what are we gonna put here? Let me just check real quick. If I go to code birch utils, let's check the .h. No, that's not right. CC. Think I did it in this project. Here it is. So this means that it's exported. And we're going to define private as static, which means that it's only for this translation unit. I'm just going to take a sip of water. Alright, so let's do this in C files as well. So this will be a public function. And let's create this is open thing. So private is open, private bool is open, and it takes a file descriptor. And how do we know if it's open or not? Later on, when we swap this OSI API and connect it to our own low-level operating system, we will have some kind of global state which has this information. But as of now, we need to invoke a system call to check if it's open. And let's see what we can use. Maybe stat. So let's see. Const char restrict path name. No, we need to have a file descriptor. Stat buff. If stat. This takes a file descriptor. And then a structure like this, which we are not interested in. I wonder if we can just give it null. that buff. I guess we can just see if it returns bad file descriptor. By the way, since we are going to use some of these in the OS API, we cannot name that thing R number. We need to have an own thing for this. So let's call it R number, like this. So we need to update this as well, R number. Okay, so let's see. Forgot what it's. So we're gonna use fstat. But we still need to have some mapping between the file descriptors. So how are we gonna do that? We are using an int 8, no, an int 16. Do we really need to have more than 256 open files? Our operating system is going to be pretty simple, so I don't think we do actually, which makes this a little bit easier. So let's redefine our file descriptor as an int 8. And then we can just create a global variable. So let's do file descriptors, and this needs to be private. And we can have 256 of those. So we're gonna have a signed integer, which we'll call POSIX-FD. And POSIX-FD will be equal to get POSIX-FD, and we give it the file. and this will always return something. Because either it will find an open file or it will find a 0. So if this is 0, then we can early return. Can just do this. And we also need to check if the POSIX file descriptor is less than 2. I wonder how we're gonna handle this standard in, standard out kind of thing. Maybe we can let is open return false in that case. So we can do an if statement here. If the file is less than 2, we return false. And if the POSIX file descriptor, well, it still can be. I think it's better to do this. Since it is a signed integer, we can check for -1. Alright, so now we need to call this stat command. So fstat, we give it the POSIX fd, and I think we can just say null here. I'm not really sure. I want to why is it complaining? Okay. So in this case we return false. Let's see the return value. -1 on error. So if this is equal to -1, we return false, otherwise true. Simple enough. So we need to define this get POSIX fd, and I'm doing this as a macro because perhaps we will change how this works later on. So this we can put inside over here. define get POSIX FD and takes an argument, and the only thing we're gonna do is return the FDs indexed by X. We need to have some include files, I guess. All right, let's see if this compiles. So we need to sync this a little bit. We need to check something real quick. All right, seems simple enough. So we need to edit our makefile for this project. Let's call this OS API. And OS API requires OS API.o, and we run make-c OS API. I think this is how it's done. Let's see. Okay, I forgot to change one thing in this makefile. We do need to have the include directory, like so. OS-API.c, OS.h. Maybe we need the full qualified path here. No, still doesn't want to go. doesn't give this though. Should we perhaps put the flags here as well? Is that it? No. Oh, it's a big C. Still the same. How do we pass that along to the other make? Because none of the flags is run. Can I get some debug output? Quite a lot. So let's see, looking for makefile. It tries a lot of different combinations. Okay, here we go. Found an implicit rule. Considering target file. Looking for an implicit rule. Must remake target. But why does it remake it this way? Do I need another switch to pass on the flags, perhaps? Here. Let's see if there is a make flag for include directories. There is similar one, included make files. Well, let's try that. So, so maybe we can do something like make flags is equal to flags. What happens then? Well, it still isn't passed along to the compiler. what if we make a rule here and says osapi.o? That make a difference? Can we make pass compiler flags sub-make? C flags. No. Maybe we need to export. Still no. It was tough to find this answer actually. But we are learning, aren't we? We learn by our mistakes. So if we do C flags is equal to flags. All right. Still doesn't work. And if we were to change into that directory, OS API, and we run make, will it make a difference? Not really. And if we add this, maybe we can do this actually. It still does not want to do that. It doesn't care what we put in here, it just doesn't pass it along. And what if we name the rule after this? Something like this. Okay, there we go. All right, we learned something today, didn't we? Too few arguments to fstats. Oh, I put the parentheses wrong. Fstat like this. And this. Argument 2, null where non-null expected. How does it know that it's not expecting a null? Maybe it's this restrict thing. But it's not here though. Well, I think we need to create one of those, even though we're not going to use it. So let's do something like this, and we'll call this underscore to indicate that we are not going to use it. Conflicting types for store. We have fd file int 8c. Maybe I got the mix up inside of here. This should be load, and this other one should be store. So we're gonna have a public int 8 store, which only takes an fd file, and at this point returns 0. Control reaches end 27. Right, because we're not done yet. Let's put return false for now. Maybe uninitialized. Okay. Let's not make it a pointer, and then we give the address here instead. Alright, so what is this? Multiple definition of R number. Because we include the header files from multiple locations. Maybe we should add to all of these a pragma once, so they will only be included once. I'm not sure it's gonna help in this occasion though, but let's try it. Nope. Since this is happening when we link, it doesn't work. So we need a way to differentiate if we are including from the main program or from the library. So let's see. It's inside of the os.h. So let's say if we have defined that we are inside of the library, then we're gonna do this. Otherwise, we're gonna do extend extern extern public error number, and if, and we're gonna do the same here. We make it public. And where do we define this library thing? That must be inside of this file. So we do define library. And now it works. Pretty nice, pretty nice. Alright, let's finish this function, shall we? So we have checked that the file is open. Now we need to read one character from that file. So we need a buffer. Let's say we have an int8 buff of size 2. And we also need to have a signed integer with the return values. So let's just call this n. And let's clean this out first. So we set buff equal to buff plus 1 equal to 0. And it should be an int8 0. And then we set n equal to the read of our, we need the POSIX file descriptor as well. So let's do signed int POSIX fd. POSIX fd is equal to get POSIX fd of file. And how do we show a failure here? If this is 0, it has failed, I think. The indices are actually the FD type, so we should make this a signed integer, actually. But then we don't have 256 different. Maybe we can do something like, we can make this an int8 instead, and this is an unsigned thing. And let's say 0 is the failure. So let's turn this back to this. And let's do if file is less than 3. So just to remind ourselves, um, so if it's a 0, it's an error. If it's a 1, then we have standard input. And if it's a 2, we have standard output. Okay. So if POS6FD is 0, in that case we return an error of bad file descriptor. And if POS6FD is, if it's 1, let's see here, if it's equal to 2, if it's equal to 1, that's our standard input. Maybe we can do it like this instead. POS6FD is equal to, if POS6FD is 0, if it's 1, then it should be 0. And if it's 2, it should be 1. And if it's 3, which will indicate standard error, then it should also be 1, because we don't have a standard error. Which means that we don't need this clause. We make sure it's never standard error. And in that case, we will set it to 2. But we need to have an else clause as well. And can we really set it to itself? I'm not sure, actually. Well, we'll see, won't we? Okay. So we're gonna read from the POS6FD into our buffer. We're gonna read 1 byte. And n should be equal to 1 if we succeed. So if n is not 1, it means an error. And here we need another error code. error. Let's just say it's a no error IO, input output error. Otherwise it succeeded. And in that case, let's see. No, I'm doing this wrong, aren't I? Because we're gonna write. This is our write function. Which means that we need to set buff equal to the int 8. No, we can set it to C like this. So then we write. If it fails, we return this thing. Otherwise, we return true. And we can basically copy this whole thing and put it here and just modify a few things. Alright, so let's see. In this case, we are going to read 1 byte. This should be if it's more than 2. I think. This becomes a little bit tricky though. Or maybe not. Let's do 3. But then we waste one place. No, let's have it as we did. Alright, so we check if the file is open. And we do this and this and this. We get the POSIX-FD. In this case, we don't set this. And we read 1 byte. And we just return that byte as an int 8. And that will be buff like this. And we need to add this IO error. Let's also create an error no error, which is 0. All right. We need to have some includes. Juni std. And it compiles. All right, so we need to have something which sets up this array. This FD's array. So let's create a private function. So private void setup FDs. So first we want to zero it out. So let's do 0. FDs. Size of FDs. What else? We need to deal with the first couple of entries. So FD's 0. This should map to the standard input of 1. FD's 1 should be 2. No. Yes. And FD's 2 will be the first open real file. So we will not touch that. And we need a 0 function. Let's put that inside of the OS API. It takes an int 8 star and an int 16 size. So private how did I define it here? Private 0, we can't do that. We need to have void here. Private void 0, int 8 string, and int16 size. So how do we clean this thing out? Let's do a simple loop. So let's create an int8p and an int16n, and for n is equal to the size and p is equal to the string. We loop as long as n is positive, and at each iteration we do n minus minus, we do p plus plus, and then we just set p equal to 0. And we return. Easy enough. This should compile at the first try. Almost. Set up FD. Okay, we haven't used it. So let's use it. I guess we can't really. What I would like to do is something like this. So we run this. But this is not possible. I don't think it is. What if we were to put this in, let's see. Can we put it? I don't think this is gonna work, is it? No. Which means that we need to have some kind of initialization function, which we always must run in the beginning. So inside of this thing, we need to have a public init it right here. And what will this do? Public init, public void init. The only thing it's going to do, right now at least, is call our local setup fds function and return nothing. Which means inside of this one, we need to do that first. Which means that we need to check if this has been done. Otherwise, we cannot do any I/O. So how can we flag that? Maybe we can just use a global variable. So it'll be public bool initialized. And this needs to be false. And if we go here, we want to set initialized to true. And we need to check that in every public function that does I/O. Or maybe we can use this is open, because this will be called in every occasion. Though this can only return true or false, and we need to show that it's because of the uninitialization. So let's put it here. We can just do some macro. Let's say assert initialized. We put it inside our load and our store, and possibly even a couple of others later on. So let's see, inside of this os.h, or this should probably be inside of here. So we define assert initialized. So let's do return error uninit, or maybe error init. That's good. So let's say we have an R init, which is 1. Okay, we run into the same problem as before. So we need to use the same solution. Alright, so let's see if it works. Let's comment out this init. And let's try to read. Let's see. Need to check which is which. Store is reading. So we store from the file descriptor 0. And we read it into no, it's like this. Let's print it in hex. Alright, let's see what happens. It's equal to 0, which means it's an error. Let's also print the error number. And by the way, in our init function, we should also set the R number to 0. Okay, so the return value is 0 and the error number is 1. And what is error number 1? Uninitialized. So that works exactly as we wanted it to. What if we were to put this back? Will we be able to read from the standard in? We still get a 1. But it didn't really recompile, did it? Maybe we should do a make clean here. In the OS API. Maybe we put it in the other one. Can we do something like clean all? Let's do clean and clean OS API. We create that, so clean OS API. We need to set this as phony. So phony basically means that it doesn't produce anything. It just is phony. Okay, so now everything should be compiled. But we still get error number 1. Why? Because initialized is equal to true. And what we do is we check assert initialize. Wait a second. Now I believe I know what's wrong. I made a stupid mistake. Yes, I return an error. I need to do an if statement first. So if initialized, then we do that. Okay. So let's test the first case again. Now it should return that error. Yes, it does. Now it should not return that error. Okay, this is going on my nerves. But did it recompile the OS API? It's included here, but it does not do that. Those Makefiles, huh? We need to check the header file as well, because that's the only thing we changed. So it doesn't want to recompile. I think it's that. Yeah. Okay. It waits. So let's type in a character. And it's returned. Our number is 0. And we get something back. It works! That is so nice. What about the other way around? Can we use the load thing to print something? Let's see. I think we should be able to do that actually. So let's see. Instead of doing this, we use the load, and this should be standard output. And we want to print, let's say, an X. And let's also add a couple of new lines. And we get an X. It works. And if we haven't initialized, in this case we should just get nothing. And we get nothing. Alright, so we have constructed our project in two different ways. We have an OS API which handles the talking with the operating system. So currently it's talking to either Windows or Linux or whatever, but later on we're gonna rewire it to talk to our own operating system kernel. And we have also created the first small steps of our command.com. So now we can start building things. And the first is going to be so we can read commands from the standard input. But that's all for now. I think this is going to be a pretty cool project, and you're going to be able to follow along on your own computer while we are developing this command prompt. So the last single step will be to create the operating system core, and then we will need to rewire it so you can run it from a virtual machine or something. But up until that point, you can run it on your own computer because of our OS API. So it's going to be a very fun project, and I hope you like and subscribe and hit the bell button so you know when the next episode comes out. And also tell me what you think about this project down at the comments. I'm very eager to hear your thoughts, and if you have any suggestions of functionality of commands that we should add to this, please tell me. Thanks for watching, and thanks for today. Did you learn anything useful today? And do you want to support this channel? Go to drbirch.com/support. You can also click the button Become a Member. Thank you for your support.